Hey, this is Mr. Ward, and this is PreAlgebra Exit Ticket 25.1 video key. And we're going to be looking at Newton's universal law of gravitation, which allows us to figure out the gravitational force between two objects, where G is 6.67 times 10 to the negative 11. That's the gravitational constant of the universe. M1 and M2 are masses of two objects, and R is the distance between the two objects. So we'll be dividing all of those factors by the square of the distance. So here is one of the objects. The object is a wombat. It's a pretty big wombat. It's got a mass of 7.7 times 10 to the first kilograms. Lives in Australia. But given the distances, we're just going to treat it as the Earth. Because what we want to know is how much gravitational force there is between that wombat and the supermassive black hole at the center of our galaxy, which has a mass of 8.2 times 10 to the 36 kilograms estimated, because it's a little hard to measure things at that distance, but we have a pretty good idea. The Earth and that black hole are about 2.6 times 10 to the 5th light years apart, and each light year is 9.461 times 10 to the 15th meters. So we're going to use a calculator, of course, for coefficients. So let's just work out some of the stuff we need. So we've got gravitational. I apologize, brief interruption, but the gravitational constant of the universe is 6.67 times 10 to the negative 11th. So we're going to be multiplying that times the two masses. Okay, so that's 7.7 times 10 to the first for the wombat, and then 8.2 times 10 to the 36. Those are in kilograms. Then we're going to be dividing this by something that's going to be squared, and this is where things are going to get a little more complicated. We've got to figure out that in meters. So we got to take the number of light years and multiply it times the number of meters. So we're going to take 2.6 times 10 to the 5th light years and put that into the parentheses. Okay, and then we've got to multiply that times the number of meters in a light year, 9.461 times 10 to the 15th meters. Okay, so, and that, things are more complicated. So we've got to do that. And that, of course, is squared. So what a mess! But we're going to do what we always do. We group the coefficients and use a calculator on them. So 6.67 times 7.7 times 8.2, and that's all going to get divided by these coefficients squared. So 2.6 times 9.461, and that is, of course, squared. And then over here, we're going to also group all our powers. So we'll have 10 to the negative 11th, okay, times 10 to the first, times 10 to the 36th, and that's all divided by 10 to the 5th, times 10 to the 15th, and I'm going to put parentheses around that because that business is getting squared. Okay, so that's squared. Whew! Now, let's deal with the coefficients first. Okay, so I'm going to take those coefficients, put them in a calculator. Okay, and I get 0.696. And I'm going to drop off all that other stuff. Now I'm going to make sure of this real quick. So I'm going to make a note of that. I'm pretty sure that I've got the order of operations organized in there, 0.696. Now what I want to do to make sure of all of that is I'm going to do the calculations separately. So I'm going to take this calculation here. Okay. I'm going to plop this in here. Oops. Clear that. Letting me do it that way, so I'm gonna let's work this out first. So we'll do this. Okay, we get that. 421.143. So let me copy pasta that over into our notes down here. Just make a note of this. And then I'm dividing that by this other business. I just want to make sure it's all legit. Okay, and I get this number. So it does look like I probably have a fairly legit number. So let me put that in here as well. Okay, and I'm going to divide that and see if I get 0.696. Just have a little worry that I might have an issue with my coefficients. I do get 0.696. So I'm happy with 0.696. So boom, I'm good with that. So now that's going to be times 10. Okay, let's work it all out. So we got 10 to the negative 11th plus 1 plus 36. So 10 to the, in parentheses, I'm going to say negative 11 plus 1 plus 36. And then I'm going to subtract. I've got going to be 2 times the 5th plus the 15th. Okay, and I'll put all that together. So because I'm doing 10 to the 5th times 10 to the 15th, so that'll be 5 plus 15. But that's squared, so that's going to be doubled. So let's work this all out. So I got negative 11 plus 1. Okay, so that comes out to negative 10. Negative 10 plus 36 becomes 26. And over here I've got 2 times 20, which becomes 40. And so I've got 26 minus 40, which is going to be negative 14. So 10 to the negative 14th power. And that is, of course, in newtons, which is important to take note. This is not pounds yet. Now, I'm going to make 0.696 10 times bigger, so 6.96. And now that's going to be, that's 10 times bigger, so 10 to the negative 14th has to be 10 times smaller. Okay, and that is how many newtons of force the supermassive black hole has on the wombat, which is probably good because that wombat's cute and I don't want to dump it into a black hole. So what we need to now do is take that, and since there are 4.45 newtons per pound, we're going to divide that by 4.45 newtons per pound, which will end up working out to pounds. So let me copy that. Oops. Okay, and that. And the, if I'm newtons over newtons are going to cancel out. And down here I'm going to be, I'm dividing by 1 over pounds, which means this is really the whole thing is going to be in pounds because that's going to flip that. Now let's work this out. So I've got to, I'm going to leave the power alone. I'm just going to deal with 6.96 divided by 4.45. And then that's going to be times 10 to the negative 15th pounds. And I'll deal with just the coefficient by itself. Okay. And we go right up here, pop this in here, and I get 1.564. I'm going to round at 1.56. So I'm going to get 1.56 times 10 to the negative 15th pounds is how much the wombat weighs in relation to that supermassive black hole. So that is that. I hope that was helpful.